So what speeds do aircraft actually fly at? Do they fly at speeds such as 1,000 kilometers per hour as may be announced by the pilots on the PA? Is that the primary reference for them? Let's find out in today's video. Welcome back to another video. My name is Deepak from Flying 101 and I aim to release a weekly video related to aircraft, flying, aviation in general. And the way these concepts are explained are meant to be quite simple to follow. If you're interested in any of this, please click that subscribe button. Don't forget to press the bell notification so you're notified every time a new video is released. So in today's video, we'll be talking about something very interesting and quite important, and that's related to the speeds at which an aircraft flies. So there are a number of speeds that are displayed to the pilots and used by various aircraft systems. Now, before we delve into the speeds, let's take a quick second to understand how this information is measured. There are something called Pitot probes and static ports. These are sensors that are mounted on the outside of the aircraft towards the front of the aircraft. And the role of these sensors is to measure the total pressure and the static pressure. We will explore a bit more about these pressures when we talk about indicated airspeed. But that's basically the role of these sensors, is to measure the pressure experienced by the aircraft. And this information is then either fed directly to the instrumentation to display the airspeed, altitude, etc. Or it may be sent to something called air data computers, which are pretty common these days on modern airliners. And the role of the air data computers is to take the data from the sensors, process it, and then determine the airspeed, altitude, all of that information, and this is then sent to the instrumentation for display to the pilots and various other aircraft systems on board. So having briefly looked at how the information is acquired and measured, now let's dive into the speeds themselves. So the first one we have here is the indicated airspeed, IAS. This is quite an important aerodynamic measure because it's the actual pressure or the dynamic pressure that's being experienced by the airframe. So the easiest way to explain this would be if we are in a moving car and if we just put our hand outside the window, we'd be feeling some pressure as a result of the relative airflow. It's exactly the same over here. The indicated airspeed is a measure of the dynamic pressure that's being experienced by the airframe, and this is being computed by the air data computers using the information provided by the Pitot probes and the static ports. So the Pitot probe is measuring the total pressure, so the impact pressure, dynamic pressure, and the ambient pressure, and the static port is only measuring the ambient pressure, so the pressure around the aircraft. We subtract the total pressure minus the static pressure, that gives us a dynamic pressure, which is exactly what the indicated airspeed is. And the indicated airspeed forms the basis for the other airspeeds. Next, moving on to the true airspeed. Now, between the indicated airspeed and the true airspeed, there are two other airspeeds called calibrated airspeed and equivalent airspeed, but we wouldn't actually get into those. They're not directly presented to the pilots, but they are calculated in the background. And basically what those two airspeeds are the speed corrected for instrument position error and compressibility effects. So having covered the indicated airspeed and we briefly touched on calibrated and equivalent airspeed, now let's understand what the true airspeed is. As the name suggests, this is the real airspeed of the aircraft through a given air mass. And the true airspeed is nothing but the speed corrected for density. That's the equivalent airspeed corrected for density. As we climb up in the atmosphere, the density of the air decreases. What do we mean by that? It simply means that there are lesser number of air molecules per given unit area of air. And as a result of this, the speed of the aircraft would be different because of lesser resistance being posed by the air, because it's got lesser density, hence there's lesser resistance being posed to the airframe as it's moving. And so it actually flies faster as it climbs because of this lower density. And that's what the true airspeed is. It's the airspeed corrected for the density. Now, let's talk about the ground speed. The easiest way to explain the ground speed would be to think about a shadow of the aircraft being cast in the ground. Now, the rate or the speed at which this shadow moves is nothing but the ground speed of the aircraft. As simple as that. The ground speed would be the same as the true airspeed if the wind was calm. However, as a result of a headwind or a tailwind, there may be some differences. So if we had a headwind, the ground speed would be lower than the true airspeed and vice versa. For example here, let's say the true airspeed of the aircraft was 300 knots. If we had a 20 knot headwind, that would translate into a ground speed of 280 knots because that 20 knot headwind is actually slowing the aircraft down by that much amount. And conversely, if we had a 30 knot tailwind, let's say, so for an aircraft that's flying at 300 knots of true airspeed, with a 30 knot tailwind, the ground speed would be 330 knots. Think about walking on a conveyor belt. Let's say if we were walking at a speed of 4 kilometers an hour and the conveyor belt was moving at a speed of 2 kilometers an hour. If we were walking in the direction of the movement of the conveyor belt, our effective speed would be 6 kilometers per hour, because 4 plus 2. So that's like going in the direction of the conveyor belt, hence the tailwind. And conversely, if we were walking against the direction of the movement of the conveyor belt, our effective speed would be 2 kilometers per hour. Just another way to explain the concept of the ground speed. And what happens is, as the aircraft is flying and it's disturbing the air mass around it, it's actually emanating pressure waves. It's noise being emanated from the aircraft. Now these pressure waves can be thought of as ripples. Think about throwing a stone in a perfectly still pond, and when the stone falls onto the surface of the water, how it actually generates ripples all around it. It's quite similar to what's happening when an aircraft is flying through air and it's creating those pressure waves around it as a result of disturbing the air just around it. Now the pressure waves could be thought of, if this was our aircraft, once again, excuse my drawings, think about the pressure waves of this nature. Now at a certain speed, the aircraft actually starts catching up with the pressure waves that are ahead of it. So instead of something like this, it would look a bit more like this. So basically the waves are now compressed. As you can see, they're quite spaced apart over here, but over here, as the speed of the aircraft is increasing, it's catching up with the pressure waves ahead of it. These pressure waves are traveling at the speed of sound. Now if the aircraft was actually catching up with those pressure waves ahead of it, it would mean that it's actually getting closer to the speed of sound. At some point, this would create shock waves, which would have quite a detrimental effect on the aerodynamics of the plane. So that would be a sharp decrease in lift and an increase in drag. And it could be quite dangerous if the aircraft was not designed to compensate for these effects. Hence, it becomes important for the pilots to know when or how far the aircraft is from the speed of sound. And this is where the Mach number comes into play. The Mach number is nothing but the ratio of true airspeed to the local speed of sound. What do we mean by the local speed of sound? It's basically the speed at which the sound travels, and it's nothing but a function of temperature. At sea level, in atmospheric conditions, sound travels at a speed of 660 knots, approximately. Now, in case you're wondering how the conversion works, 1 knot is 1.852 kilometers per hour, and in case you're thinking about miles, it's 1.15 miles per hour. So at sea level, atmospheric conditions, standard conditions, we're talking about sound traveling at a speed of 660 knots. As we climb, the temperature decreases, hence the speed of the sound decreases. And the Mach number is simply the true airspeed divided by the speed of sound at that temperature. And in case you're wondering how the speed of sound is calculated, just a fun formula here, it's 38.95 multiplied by the square root of the outside air temperature. SAT represents static air temperature, but it's nothing but the outside air temperature, in degrees Kelvin, not centigrade. And the conversion is just adding 273 to the centigrade value. That gives us the Kelvin value. Square root of that multiplied by this number gives us the speed of sound. So true airspeed divided by this speed of sound is what gives us a Mach number. Now the Mach number is quite a significant measure on high performance jets for the reasons that we talked about in terms of the creation of the pressure waves, which then in turn lead to the creation of shock waves, which could potentially have quite a detrimental impact on the aerodynamics of the aircraft. And the way this information is presented to the pilots and used by various other aircraft systems is such as Mach 0.78, Mach 0.80, depends on the aircraft type and the speed it was flying at. But this number, let's say Mach 0.80, is nothing but the percentage of speed of sound at which the aircraft was flying. So if it was flying at Mach 0.80, it basically means that the aircraft was flying at 80% of the speed of sound at that temperature. If the indication was Mach 1.0, it would mean it was flying at the speed of sound, but that's not what we typically see on aircraft, because it was only the Concorde really that used to fly at speeds greater than Mach 1.0, actually up to Mach 2.0 even, so twice the speed of sound. But yes, today's commercial jets usually fly within the transonic range, so we're talking about speeds less than Mach 1.0. Alright, so there we have it, our little summary of the various speeds that an aircraft flies at. Remember, these are just not for presentation purposes to the pilots, but they're also used by a number of systems on board an aircraft, so they are quite important. Alright, so I hope that made some sense and it wasn't too difficult to follow. If you have any questions, comments, or you would like a certain topic covered in relation to flying, aviation, etc., please put that in the comments below and I shall do my best to cover that in a future video. If you like the video, please give it a thumbs up, share it along. Thank you very much for your time, and I look forward to seeing you next week when we shall talk about deceleration devices, how an aircraft decelerates after landing. Thanks very much again, and I wish you a great day.